So we're going to kick things off. Our fearless consortium leader, Niels Warburton, will be talking about the consortium overview.
Great. Thank you very much. It's a great privilege to be here to speak on behalf of the LISA Consortium. Today I'm going to give an overview of the consortium, what its structure is, because things have changed a lot since the last LISA Symposium and the adoption of the mission. Give an update on some of the work we're doing and where we're planning to go in the future. I think when thinking about where we are, it's good to think about how we got here. Nora started with a history of the mission, and so this is something similar, but I've highlighted the organizational structure that have existed over the years. So ideas about doing space-based gravitational wave astronomy go back into the 70s, and the first mission proposals were in the 80s. And then, as Nora said, in 1993, the first proposal was put to ESA, which was the MV proposal. That wasn't accepted at the time, but it led to the formation of what was called the LISA study team, which was a body that was designed to kind of progress the mission. Fast forward a few years, NASA joins, and in 2001, we have the LISA International Science Team becomes the governing kind of body. And then the first mention of the LISA Consortium itself appears in 2012. And back then, it was really formed by a sort of group of PIs that are leading the mission. It wasn't open to everyone. We then, of course, have the launch of Pathfinder, the detection of gravitational waves. And in 2018, the LISA Consortium opens to all members of the community and with full and associate members, as they were called at the time. A little further forward, we have the adoption of the mission in 2024. And that led to the formation of the LISA Science Team and a bunch of other structures. And that necessitated a restructuring and reboot of the LISA Consortium, which I'll explain in this talk. And then, of course, we look forward to the launch of the mission in 2035. OK, so we've seen diagrams like this before, but post-adoption, we now have a bunch of different structures. And this necessitated restructuring the LISA Consortium because in the past, the LISA Consortium was the body that overlooked some of these structures, but now they've been taken over by various aspects of the project. So of course, we have the space agencies and their industrial contractors who are now building the mission, so they look after that. But also one of the activities that the consortium looked after in the past was these kind of mock LISA data challenges and preparing to carry out the analysis of the LISA data. And that has been absorbed into this thing called the Science Operations Center, and we've heard talks about this. On the European side, we have the Distributed Data Processing Center, and on the NASA side, we have the NASA Science Ground Segment, and Tyson gave us a nice overview of their plans there. There's also been the creation of the LISA Science Team, and Valeria gave us a nice overview of what they do. They guide the scientific focus of the mission. They will set up their own working groups. They'll also set up science topical panels later that will do some initial analysis. And then over here, we have the science community, and within that, the LISA Consortium. Now, I want to emphasize one thing. The science community really covers this whole box. Like, we're all part of the same community. But of course, there are reasons it's drawn this way. The LISA Consortium sits within there, and its role is really to support the scientific community and the output that's going to come from the other parts of the mission. We've had lots of talks and plenary talks from people throughout the symposium, and I've put them, anyone who put their picture on the website at least, I put them in roughly where they belong for the different parts of the project, although actually many of us wear multiple hats. And so some of us might be in this part of the project, but also in this part as well. OK, so this change of structure necessitated a redesign of the consortium, and a group of us, about 60 of us, undertook that in 2024 and 2025. And that led to a new structure for the LISA Consortium that I want to spend a little time explaining so you can know how you can engage with that where we are. OK, so first of all, the thing we spent, these are just 2 paragraphs, but we spent a good few days agonizing over the words of these, as some of us might remember. So what is the consortium? There were lots of options before us. It could have been much more looser. It could have been much more tied together. But in the end, we settled that the consortium is going to be a scientific collaboration that works together collaboratively to maximize the return of the LISA mission, in particular, working with the LISA data. We could have been a different structure. We could have just been a support body that just supports the broader community. But we decided that we would work together to work on the LISA data. And we are committed to the long-term growth of the community. I think that's something unique to the consortium of all the pieces of structure. We really think about the consortium, but also the broader community and supporting them and growing them. We want to be supportive and inclusive as we do that, and we want to offer training and prepare people to be ready to use the LISA data, whether they are in the consortium or not. And in particular, we're focused on early career scientists because they will be the ones doing the analysis when we have the LISA data. So we want to support them as much as possible. So that's the overall vision, and I'll come back to that towards the end. But in terms of what it means to be in the consortium, we have two types of members. So the first thing to say is that a major change, and it's something that's different from other scientific consortia, is that all members join now as individuals. You don't need to form a group at your university or collection of universities. You join as an individual. And once you join, there are two types of membership. You can be a core member, which is where you're dedicated to being engaged and committed to actually supporting particular deliverables of the working groups and the relevant projects. With that then comes rights. You get to vote in the leadership elections for the consortium. You, of course, get authorship on the relevant papers and authorship on consortium papers when they come. Comes with duties, as rights always do. And the duty is you must report what you've been working on, basically. Each year, you must say, well, this is what I did in the past year. And of course, you must follow the various policies set by the Consortium Council. In terms of reporting your work, we're not too onerous about this. We try to be light touch. What you do at the end of each year is you just write a few sentences or a paragraph explaining your contributions to the various projects you're involved with. That then goes to the various project coordinators who then just say, yes, I can see this person did this work, and they sign off and say, that was your contribution to the year. We don't count FTEs, at least not at the moment. We suggest roughly 25% of your research time should be spent on consortium activities in order to be a core member. If that doesn't look like you, if you're saying, well, I'm really interested in the mission, but I'm not ready and I have the time to contribute right now, I'm not going to focus on consortium projects right now, but I wish to remain pretty engaged, you can be a community member. These are more passive, but we keep them in touch with things. They get invited to consortium meetings, and hopefully in the future we might encourage some of you to become core members. So those are the two types of membership. I just want to explain now the structure of the consortium itself, so you can understand how it's governed. We've tried to create something which I think is quite democratic, where we hope voices can be heard. And so let me just explain what happens when you join the consortium. So we have core members, and they, as I say, join as individuals. And once you join, you organize yourself in various ways. So everyone must choose a working group to be part of, and we have a whole bunch of working groups. So on the science working groups, we have astrophysics and cosmology, data analysis, research and development, fundamental physics, instrumentation, simulation and processing, and waveforms. We have two other working groups that think more about the health of the community, which is the early career scientist group, and the communications group that handles comms inside and outside the consortium. Once you join, you can form into a member group. You can say, well, I'm here with a bunch of people from my own institution. I can form a group within the consortium. The consortium itself is governed by a council, which is made up of representatives, I'll explain in a moment. And this is the body that debates and passes motions and decides what the direction and the focus of the consortium should be. And it's made up of representatives of the core members. The way that works is if you form a member group and you get large enough to have 10 members, then you send a representative to that council. But if you've joined as an individual and you're just one or two people at an institution, you still get representation via your working group. So everyone should be represented on the consortium council, and hopefully that's a way that you can be involved in the decision-making process of the consortium. So the council creates a motion and says, we should do this. Who actually does it? It's not the council. So the first line is the management team, which is like the executive of the consortium. This is a group of at most 8 people who carry out the will of the council to ensure the work gets done and handle the day-to-day running of the LISA consortium. There are 2 elected members to that. One is the consortium spokesperson, which is myself, elected by all core members for a 2-year term. And then we also have a nice connection to the project where we have the LISA science team representative who's elected by members of the council who represents or acts as communication between us and the LISA science team. At the moment, that's held by John Gare. The management team is only 8 people. We also don't carry out the work of all the consortium. So we have a selection of committees that sit under the council that carry out work. and advise on policy. And when we need to, we can also create small teams that carry out other tasks. It's called temporary task teams, like running a conference or something. So there's a lot of structure there and arrows and boxes, but we have over 1,000 members in the consortium, core members, and we have 750 community members. So you need a lot of structure just to organize the work of the consortium. Okay, so let me introduce some of the people there. I've tried to put as many faces on here as possible because if you want to talk about the consortium or its research, you can come to me, you can come to people here, or if you know someone, then hopefully that's a great first place to make contact and talk about what's going on. So here, let me just briefly introduce the management team. We have myself as spokesperson and John as the LST representative. We have Kelly as our deputy spokesperson. Suzanne looks after communications for us. Tamara and Daniel are our liaisons with the science working groups. We have Gianluca, who looks after membership and service tracking and infrastructure, and Shane looks after the health of our community. We also have 2 council co-chairs elected by the council who join us, and that's Richard Brito and John Regan. As I said, we can't do all the work by ourselves. We also have a whole bunch of committees. I really wanted to highlight these committees because they do so much great work, and it's so often not seen. But the day-to-day running of the consortium, they're doing a lot. I won't introduce everyone here, but just briefly to say we have an appointments and elections committee. They run the elections and handle the appointments into other committees. They work with the DEI committee on that. We have a bylaws committee that handles thinking about changes to the bylaws of the consortium. We have a membership committee that when you join, they're the people who look into your membership application, and they also deal with all the service tracking, so they've been very busy recently. They're doing a lot of work at the moment. And then very recently we formed a publications and presentations committee, so we need to start thinking about how consortium projects authorship is handled and things like that. We have some basic rules, but we need to develop that further. As we heard yesterday from Hontus and others, we also have a DEI committee that does work like surveys, that tries to encourage diversity throughout the consortium and helps run events like we saw yesterday at the Consortium and Symposium. Great. And then the next level of management that's very important is the working group co-chairs. So each working group, typically, not always, has 4 co-chairs associated with it. And I think there was a question there about early career representation and management. So one of the key things that we've had in the LISA Consortium for a long time that I think has been very effective is we also have 2 senior co-chairs and we also have 2 early career scientist co-chairs. This is a great way to bring early career researchers into learning about management. So everyone here whose circle is blue is a senior researcher, and everyone who is yellow or orange in the circle is an early career scientist, as defined by Lex. And so pretty much all of them have 2 of each. Another good thing to highlight as well is I think we saw in the statistics yesterday the consortium has 26% of its members are women, but 40% of our leadership here is women. So I think that's something we should celebrate. These are all elected. The individual co-chairs hold individual working groups hold elections every so often to elect the co-chairs in a rolling cycle. And again, if you're interested in getting involved with the consortium more, and you're in a particular area, these are the right people to reach out to and have a conversation about which project you might want to do. Okay, I didn't want to talk just endlessly about organizational structures, but I think it's important, especially as things have changed a lot in the last couple of years. Let me just give a little bit of sample of some of the projects that we're doing in the consortium so you can see if the kind of work you might be interested in. So consortium projects are collaborative efforts that are open to all core members. So you can't join the consortium and just do your own little LISA thing and get credit for that. You have to do it in a way that involves, it's open to all members of the consortium. Currently we have about 60 projects that are active within the consortium, and that's growing. And there are various deliverables. Sometimes those deliverables are to study something and write a paper. But as we're moving closer to having a mission, we get deliverables like produce codes that can be used, we produce technical documents, and in the future we'll start producing pipelines to do analysis with the LISA data. So let me just give a little overview. These are just picked. I asked the working group co-chairs, can you just pick some projects? But I obviously can't show all 60. And I've tried to pick a bunch that are kind of in different stages of development. So you can see, some projects are just starting, some projects are finished, they've got papers and they're moving on to new things, and things like that. So in astrophysics, one project, which is actually joint with the waveform working group, and this is something we're seeing much more of now. I would say in the past, working group projects were kind of within their working group, but we're seeing a lot more crosstalk between the working groups, which I think is very natural and great to see. So here is a project where they're trying to define for the people doing waveform modeling what the parameter space is. So waveform modelers are always saying, do we really have to model eccentricities of 0.9? Like, do we need to do that? That's hard. Like, and if you tell us we need to, we'll do it. But if we don't, maybe we can focus on something else. This is a very hard problem. Astrophysics is complicated. But there's a project here, and you can see kind of how this works. At the beginning, they're looking to recruit people into the project. They'll then start identifying the milestones. They'll start collecting together codes and trying to survey the space and work out what can be done. If there are gaps, they'll try and think about how they might fill those gaps. At some point, they'll hand off some sort of best guess to the waveform working group who can focus on development of those models. And then what's nice to see as well, they also reflect on future work. This will be an ongoing process as we learn more about the astrophysical environments that our sources live in. Another working group, this one, the communications working group. So you've all, I'm sure, seen or heard from them. They've been very busy during the symposium. They do work both internally for the consortium, but also explaining the work we do to the wider world. So one thing they do, and they had a really great newsletter a couple of months ago, and there's another one coming out soon, is they publish a newsletter, which is just open to anyone. You can sign up to that. I'll tell you how to do that at the end. They run our social media, so they run campaigns, like for the LISA Pathfinder mission, they ran the 10th anniversary celebrations online. They also try and promote individual members of the consortium. We have this Humans of LISA program. And they also run the community talks, on the Monday talks. There's a really great talks that happen pretty much every Monday, where they talk about project work that's in the consortium, so you can see what's happening, or just exciting papers that have come out recently. And those talks are fully booked out until like September and beyond. So they have a lot of interest in doing that. And then they follow up on social media afterwards. Another thing that they're looking at now is that now we have these simulated data sets appearing. They're looking at sonifying them, so turning those into sound. You've probably all heard you can turn gravitational waves into sound. This is great for public engagement. But looking to do that at the level of the whole data set, so it'll be interesting to see what that sounds like. It's probably a big mess. That's a new project, and if you're interested in getting involved with that kind of work, you should reach out to them, and they're definitely looking for more people to help them out. For cosmology, I picked a project which is actually a synergy with another gravitational wave observatory. So here they are doing a project with members of the Einstein Telescope collaboration. They're looking at injecting and recovering the parameters for a particular stochastic background. And what they find in this particular case is that if they do it with just one of the instruments, so just using LISA, they get very wide posteriors. If they do just with Einstein Telescope, they also get very wide, but if they combine the results for both, they can do significantly better and really nail down the parameters of that. So that's a nice example of how the LISA consortium is collaborating with other gravitational wave observatories. Fundamental physics, they give me a lot to talk about, which was nice. So they focus on things like parameterized tests of GR. So this is something that grew out of the working group, and now there's already a paper that exists about this, where they're parameterizing the in-spiral and trying to see how well they can measure the deviations from general relativity during the in-spiral of a massive black hole binary merger. They're also following up that work. So they produce a paper. It doesn't just end. The project continues, looking at what happens with systematics, where if you inject a numerical relativity waveform and then recover with one of the latest SCOB models, when you do that, because it doesn't perfectly match numerical relativity, and we have very high SNRs for these massive black hole binaries, you're left with some residual. And this residual can then induce biases and parameter deviation estimation, and they're interested in whether or not they can lead to a false claim of deviation from GR. They also do work on gravitational wave memory, which is this effect where after the wave passes, there's a permanent deformation that's left. And so there's been quite a few papers there looking at that in general relativity, whether or not you can actually make detections with a single source. Normally we think about stacking sources to find this particular effect, but with LISA there's a prospect of doing it with just a single source, and also looking at what that looks like in extended theories of general relativity. Finally, the waveform working group, which is actually where I am as a researcher. There's a couple of projects here. We're fortunate to be in a place with LISA where we have a lot of great waveforms that have been developed to tackle the ground-based problem. But we have a much broader parameter space. We have potentially louder signals. And so there's a lot of challenges with taking those models and pushing them out and ready to use for LISA. And so studying the systematics that we get from that is important. This isn't actually from the working group, but I think it just nicely highlights the issue. This is a recent paper by Mahal Petra and collaborators, where they show that if you inject an NR signal with a mass ratio 18 and then use the best models we have from the ground-based sources, this is a processing system, then you get pretty significant biases in your measurements, right? And we expect to find a long tail of massive black hole binaries and IMRIs and things where you're extrapolating the models which are normally calibrated for mass ratios less than 10. In terms of Emory modeling, we also have a sort of big community effort to take all of the codes out there doing black hole perturbation theory, cross-compare them and produce a kind of final data set that will be used in order to drive the calculation of extreme mass ratio in spirals. And so that's a nice one because it has about 20 or 30 people working on it because we have a lot of these codes around the world. And it's a great opportunity to bring together all of those results. Okay, so that's a lot of the individual projects that exist within the consortium. But as we heard, we're going to soon have simulated data sets to analyze. And of course, eventually we'll have the LISA data. So the first year of the LISA data, when it comes, will be a protected period. We won't have access to it. That'll be analyzed by the science topical panels that will be set up by the LST. They're still, I know, discussing quite how that'll be done, but that's for them to decide. But after this period, the science ground segments will just continue to run their global fits and produce descriptive catalogs of the signals in the data, but the interpretation of that data is then carried out within the wider scientific community. So the goal of this sort of key project, this basically larger project within the consortium, is to lay the groundwork for this downstream analysis. So I think it's useful to think about the different components and what's happening. So in the science ground segment, and I've just amalgamated the two into one here, we will have the LISA data coming in eventually, but in lieu of that, there's something called the Coordination Unit for Simulation that develops these simulated data sets that we're going to analyze. That then passes to L1. Jean-Baptiste will talk about that after me. It then goes into the global fit that Tyson talked about, and then it goes into various global fits are consolidated into a catalog, and Astrid talked about that. And then that catalog is released into the community. And over here we have the LISA Consortium with a subset of its working groups. This future project is about saying, well, what we need to do is take this catalog and carry out that future analysis. We want to look for additional corrections to physics. So we want to build a sort of consortium catalog. So we might look at, is there environmental effects there? Are there beyond GR effects there? Is there, can we use extended vacuum models? Look for cosmological backgrounds. We can also do population analysis, saying, well, now we have this catalog. What does that tell us about the underlying population? In order to do that, we will need the various working groups to think about, well, it's great you've modeled your accretion disk, but can you now put that into a model we can use in a waveform that can then be built into a waveform that is sent into the data analysis group? And we can do this with all the simulated data as it appears. We have these data sets. You've heard about mojito, the various other alcoholic beverages that will be coming out of the science ground segments. We will attempt to analyze them in preparation for the real LISA data. And when we do so, there'll be hopefully a nice feedback loop. So we will analyze them, say, well, the data was in the format we could use, or we needed extra data to do this science, and then we'll feed that back in, and they will then update what they are supplying in the catalogs. And that's going to be great because it's going to tie together a lot of the projects in the consortium. Okay, another thing the consortium does is it organizes meetings. So the LISA Symposium is not something we've always organized. It's normally been organized by the Gravitational Wave International Committee, but now the consortium is sort of rebooted. We're going to sort of share that role with them. This is a long-running series. It's been going on since 1996, and it's been great. I'm sure it's been very important in bringing together the community and then the success of getting the mission adopted. This is now the 16th LISA Symposium, so we've been at this for a while, but we're more than halfway there, because roughly the 22nd LISA Symposium, maybe the 23rd, the plenaries will be dominated by the results from the LISA mission. It's not that far away, which is very exciting. I wanted to take this time just to say a huge thank you to the current organizers. So the local organizing committee, we have Peter and Anne, with Ira, Elizabeth, Bernard, and Cole, and I'm sure there's a whole large organizing team behind them as well. Also to thank Shane, who is the chair of the Social Scientific Organizing Committee, the comms team, and many more people. I organized the last LISA Symposium, and I know how much work goes on behind the scenes that you just don't see. So can we have a huge round of applause to thank our host this year? And of course, thank you to all of you for attending. In terms of the next symposium, hopefully you saw, there was a poster up. We have an open call to host the next LISA Symposium. Over the years, it's been in many different places. By tradition, it tends to move between the US and Europe, something that has always done. But we're open to applications from anywhere. That call is currently open and will close in October. And we will then let you know where the next symposium will be in 2028. In the future, I'd love to be in the position to tell you at the end of this symposium. We didn't quite get our act together in time, but that's the goal in the future. If you can't wait until 2028, don't worry. The consortium is planning to hold its first consortium meetings post-reboot. This is going to be open to all consortium members, a little bit different from the symposium. It will focus less on talks and much more on the working group projects. So the working groups tend to have their own meetings. This is going to bring all those working group meetings together and focus on the projects. It'll be an exciting time because we expect the first public release of the Mojito data set and catalog around that time. So that'll be good. The call for that is currently open, but it's closing at the end of June. So if you're keen, you should get an application in. And we will advertise the location, hopefully, and the dates in late July. Okay, so I gave an overview of everything that's in the consortium, and just to sort of conclude with a few thoughts. If you're not currently a member, or even if you are and you wish to change membership type or work on a different project, if you've seen things you'd like to get involved with and you know the project that you want to do, join as a core member. Great. I would say if you're really keen to get involved in the project, maybe you know the area but not exactly what the project is, or maybe you have a project that you think you could do collaboratively with other members of the consortium, then a great first thing to do is to talk to the working group co-chairs for that relevant group to find a place for you or that project. And finally, if you just like to remain involved, but you might be quite busy right now, but you'd like to contribute at a later time, then I strongly recommend community membership for you. And as I said, you can still then come to consortium meetings if you like. If you want to sign up, then the address is there, directory.lisamission.org/register, and if nothing else, you should sign up to the newsletter, which comes out 4 times a year and just gives you big updates, not just from the LISA Consortium, but also from the project, the science ground segments, the LST, and things like that. So just to conclude, I wanted to return to the vision for the consortium, where I've highlighted a particular word. During the symposium, we've seen all these great talks that talk about all the fantastic science and engineering that's needed for the mission. As a theoretician, I'm blown away by the engineering. It's amazing to see. But all of the science we do, all of these kind of merging black holes and galactic binaries and astrophysics and fundamental physics and all this is really fantastic. But in the end, science is done by scientists and engineers and people. Our goal in the consortium is to build a community. We want to grow that community. We want to help that community organize itself and hopefully have a good time while we're doing it. Thank you very much.
We have maybe time for a quick question or two, if anyone.
Okay, I'll give you all a chance to come up with your questions, but I wanted to thank Niels because when we started organizing this, he had kept ridiculous data on the last LISA Symposium, including like how many people were early registrants, what country everybody came from, how many students there were, and when you're trying to figure out like setting the registration fee and coming up with a scheme, that kind of data was invaluable. So just want to thank him for all the support along the way for this, and to encourage all of you to be thinking about hosting the next one. So thank you very much. And also, the consortium, one of the roles of the consortium, you did point to this, but we had social media posting that was going on during this, and all the recordings and the YouTube live stream we didn't have easy way to do that, like through the agencies. We could have done it through this university, but it was much more appropriate to do it through the consortium. So the consortium provided that service to all of us, and in the background, we've been getting lots of inquiries about what about the recordings, how do I watch the live YouTube? That was provided by the consortium, and I don't know, frankly, what we would have done if the consortium had not provided that. So just some notes on the communication service that the consortium provides to everyone. Thank you. All right, now come up with your questions.
Any other questions?
I was curious, do you think, are the LISA Consortium and LISA Symposium meetings going to like dovetail for the until launch kind of thing? Or do we think symposium meetings may become, annual now with adoption?
I think the plan currently is that they would dovetail effectively. So the symposium is different because it's open to the broader community. It's a great way that we grow our community. And so that's about bringing in new people. The consortium meeting will focus on more on the work of the consortium. So the idea there is a bit more of a workshop. There'll be some talks, but a bit more opportunity to bring consortium members together to organize the work of the consortium.
Thank you. I think you did such a great job talking about the consortium and letting folks know how you can get involved. I just wanted to add one quick thing, and that is, if you think you want to join the community, but you don't know yet what you want to work on, and you're shy visiting the working group folks, or you don't know who they are, you can still join as a core member, and you get about a year to find your place. And during that year, one of the things we hope to roll out is a way to onboard you into a consortium. So there's a whole plan to do that, and if you have suggestions for how it might be great to increase training or the specific activities that you want to do to get involved, please let us know. So join.
Thanks, Kelly.
All right, well, I think we should keep moving to try to keep someone on schedule, but let's thank Niels again.
Thank you.
Our next speaker is online and ready to go. So next speaker is Jean-Baptiste Bayle. He's going to be speaking about gaps and glitches in LISA data.
Hi, thanks. Thank you. Not exactly, actually. I'm going to talk about how we built the TDI data that you know and love in LISA. So it's going to be an overview of this L0 to L1 processing. If you don't know what that is, don't worry. I'll explain everything. I just wanted to start by thanking the organizers for giving me this opportunity. I'm very happy to be here. I'm very sorry I couldn't be with you in person, but I hope that will work out. My name is Jean-Baptiste Bayle. I work at CA in Paris, and I will talk about this TDI stuff. So I will start with a brief overview of what TDI is and what the different solutions were invented and what problems they tackle. And then I'll focus a little bit more on actually concretely how we do this for LISA. And I will on the way mention ongoing work, investigations, and I'll also try to pinpoint the different parallel sessions that are connected to L0, L1 processing and TDI. I might have forgotten some of them or some ongoing work. I'm very sorry in advance if that's the case. But okay, let's start. So this is the LISA mission concepts that you've probably seen many times now from the raw measurements that we get from the constellation, LISA, the spacecraft themselves. We call that level 0 data. And then it undergoes some kind of processing step or steps that produces level 1 data, which is often we say science ready. And with this level 1 data, we can do all the amazing global fit detections, parameter estimation that are then used to build the catalogs. You've heard Tyson talk about that 2 days ago. So in this talk, I will focus on that step, this processing that takes as inputs level 0 data and produces the TDI data, the level 1 data. And I'll start with this overview of what the big problem is for LISA. So, as you probably know, we need a very, very sensitive instrument. And one of the problems is that we use light interferometry, and our laser sources, they have intrinsic frequency instabilities. We often call that laser noise. It's not that big of a problem for ground-based detectors because they are equal arm Michelson interferometers, so that the light that propagates along both arms basically experiences the same delay. And so if you're right in a very, very simplistic way, your phase at the photoreceiver, when you recombine the two beams, you have this laser noise that cancels out by design. And so that's how we can measure gravitational wave strains of 10 to the minus 20 with laser sources that are only stable at, let's say, 10 to the minus 13. Yes. Unfortunately, for LISA, that doesn't work. The arms of the constellation is driven by orbital mechanics, and there's no way we can have a perfectly equal constant arm interferometer. So we have to deal with this problem, and if you optimize the orbits, you get something like this. So in the bottom plot, you can see the light travel times. So it's another way to say the arm lengths of the constellation across 10 years of mission. And they vary by a few percent, right? I think it's about 3 to 4%. Around this average value of 8.3 seconds, which is the equivalent of 2.5 million kilometers. And so if you write down the same equation and you're trying to find out or to work out the power due to this laser noise at the photoreceiver, you find something like that. So something that is proportional in power to the arm mismatch squared times your laser noise PSD. And so at 1 millihertz, for an arm mismatch of 0.2 seconds, which is about this few percent of the 8.3 second arm that I mentioned before, you find a laser noise of about 10 to the minus 15, which is many orders of magnitude above your expected 10 to the minus 20 and below gravitational wave signal strains. So this is basically another way to see it. You have the LISA band here presented. In gray, you have the raw laser noise. So this is, of course, illustrative only, right? This is a simple model where we have a white laser noise. And so if you take the raw measurements that we actually have at the interferometers, you get this yellow curve or blue curve. It depends if you do a back and forth between your arms. And if you do the usual Michelson stuff, what you get is the green curve. And what you want to be at is this dashed blue line. So you see many orders of magnitude above. So you need to find a solution. And the solution was actually thought about many years ago. In 1996, that's I think the first time people started talking about this. And the idea is instead of having a single interferometric measurement, you'll have two, right? One, which I denote here Y1, basically measures what happens on the first arm, and another one for the other arm. So you have two measurements, Y1 and Y2, and you can write what they are in terms of laser noise and, of course, gravitational wave power in the frequency domain. And you can see that if you manage to apply filters and work out this or combine them in this way, so this Y1 some filters minus the other one with another filter, you get rid of this laser noise. And you're only left with your gravitational wave signal, of course modulated by a certain filter. That works well in theory, but actually, because laser noise is so big compared to the signals that you want to measure, you need exquisite precision in terms of filter application. And so people have shown that if you want to get to these 10 to the minus 20 in terms of strain sensitivity, you need to integrate your signal, you need to integrate 6 months of signal, which is not practical. But if you assume some things on your arm length, typically that they're not varying, that they're constant here, you can find a time domain solution, which is linear time invariant, and you can build 2 combinations, these Y1 minus Y2, and this delayed Y1 and delay Y2. And if you work out what kind of laser noise they have the same. So basically you can do the first line minus the second one, and again you find some kind of laser noise free quantity, which looks like a synthesized Michelson quantity. Okay, so that's a win, and that's basically the idea behind time delay interferometry. We have one caveat is LISA's arms are very, very long, and so you can't really just put a mirror at the end of an arm, because if you were to do so, the received power on the way back would be so small. And so what you have to do is send a fresh laser beam that acts as a transponder. But of course, if you do that, you have a fresh realization of your laser noise. So everything we talked about does not work. So you have to find a way to, at the same time, reconstruct this reflected laser noise and compute your TDI combination. And you can actually do that. You can convince yourself with this little schematics. So here I have an arm, a very long arm. On one side I have laser noise P1, and on the right side I have P2, the yellow one, which are completely independent. And if I work out what I measure on both sides, this Y1 and Y2 again, you can show that you can synthesize a transponder. So as if P2 was just a mirror reflecting P1 by computing this combination of delayed Y2 minus Y1. And so if you've done that, you win. We basically get back to previous case, and we know that we can apply TDI. So that's a, let's say, hand-wavy historical way to demonstrate exactly what is TDI. But the bottom line is that we can reconstruct offline Michelson variables, or things that look like Michelson variables, laser noise free, by linearly combining time-shifted interferometric measurements we get from the LISA constellation. So the L0 data. Of course, you can have people started to find a formalism to compute these combinations, and Durandar et al. In 2002 came up with this algebraic formalism for this. In the end, they find that the TDI, aka laser noise free space, is a module that can be generated by 4 specific combinations. You're free to choose the basis, but usually we use these 4 Sagnac combinations, alpha, beta, gamma, and zeta, as the basis of the TDI space. Out of these 4 generators, only 3 are independent, because we have a linear combination such as the one showed here. So basically, only 3 combinations is enough, or let's say, is everything you can get in terms of laser noise-free observables. So these combinations are quite complicated. They involve delays and measurements. But there's a, let's say, an intuitive way to understand what's happening, and that was proposed by Michele Vallisneri in 2005, which is that you can factorize the expressions of these combinations and interpret what's happening in terms of geometrical combinations. And typically, the Michelson combination that we've talked about can be seen as two beams propagating along the two arms. You've seen the animation on opposite directions, and then we subtract them. And so from this, you can imagine a lot of other laser noise canceling combinations. Some of them actually only use two of the links, so they might be useful in case of link failures. But there's a vast zoo of these combinations. And these are the geometric interpretations of the alpha, beta, gamma, and zeta combinations. I talked about these generators of the TDI space. So of course, alpha, beta, gamma are deduced from one another by cyclic permutation of the indices, and zeta has this interesting symmetry properties. So that's basically the theoretical basis. Now I'm going to talk about how we do this exactly for LISA. And we have one more caveat, is that, as I said before, the LISA constellation is breathing. And we have these time-varying arm lengths, and in the entire derivation of the TDI generators that I presented before, I said that we assume that the delays are constant. So everything we use to come up with this TDI space and these four generators basically break because delays do not commute, so you cannot talk about a module. And the traditional combinations cannot cancel laser noise exactly. They do cancel, or they do suppress laser noise, but if you look at what's happening on the right side here, so in orange you have, let's say, the usual 0th order Michelson, and as we said before, it's not enough by far. And if you use the TDI 1 combination, the one that I presented before, you have this dashed blue line. The solid blue line, which is above what you want, which is the dashed blue line. So it's not enough, basically. The residual laser noise from these TDI combinations is not enough. It's about an order of magnitude above the requirements. So we need to find new combinations, and Tinto in 2002 proposed a recursive algorithm to basically promote first order combinations to second order combinations, which can account and handle the breathing of the constellation, so the time varying arm length to first order. And we usually call these combinations the second generation combinations. So typically you can take Michelson combination X, promote it to second generation. And a way to see it is geometrically, you basically go around all the arms once again. And if you do this, then you find the TDI2 curve, which is the green curve on the right plot, which is now well below the requirement curves, which is the dashed purple line. Of course, you can imagine you can go to higher order, right, combinations, but it's been found that it's sufficient to go to second generation, as we see here. So usually we use these second generation combinations. Of course, each of these combinations, they have different noise and signal transfer functions. In the case of a static equal arm constellation with symmetrical noises, and usually when we say that, we talk about the dominant noises, the ones that are not reduced by TDI, you can find three combinations for which the noise covariance matrix is diagonal. So that's super useful for data and analysts. And we usually call them orthogonal combinations, AET. Of course, in realistic cases, the arm lengths are not equal and not static, and the noises will not be symmetrical. So AET will not be really diagonal. So there will be off-diagonal elements of about a few percent because arm lengths vary by a few percent. This T channel is often denoted as the no channel because at low frequencies, it's actually quite insensitive to, at high frequencies, it's actually quite insensitive to the gravitational waves. Note, however, that it's not a good null channel at low frequencies. So you cannot use it to characterize the instrumental noise directly like this. And there's been a couple of studies about it. Muratori et al. In 2022 measured this, and you can refer to these plots. Also, these non-diagonalities, they play an important role, especially when you try to fit noise or stochastic gravitational background. So in the realistic case, in the real case, I would say using AET for data analysis is not a good solution if you want to have a precise parameter estimation. Something interesting is that you can show that you can find specific optimal combinations if you want to look for specific sources in specific sky locations. So you can do some coherent source tracking by switching combinations as the constellation moves to always pinpoint to a specific location in the sky. Interesting enough, this argument can be inverted and you can find close to zero response combinations for certain directions. So unlike T, which is a bad null combination throughout your sensitivity, you can find specific combinations for a specific direction in the sky whose response to gravitational waves is very small. That was found out by Tinto and Shane Larson in 2004, and it's been extended by Barroso et al. In a couple of years ago. And yeah, that's also an interesting field of research. So that's a big question and an ongoing question as well, which is what combinations to use. Of course, theoretically, you don't really care, right? You take 3 combinations that are not entirely correlated, and that should span the entirety of your TDI space. But some combinations have other properties that are desirable. Typically, you can see here that as time goes, the T channel itself is very sensitive to your arm variation. So it's probably not a good choice. You can also see, or you probably know, that these combinations have zeros at high frequencies, and doing data analysis around the zeros is complicated. So, yeah. In the realistic case, we also have another problem, which is that we don't measure test mass to test mass quantities, but we use the split interferometry. I think it's been presented on the first day. We basically measure spacecraft to test mass, and then spacecraft to spacecraft, and then the last bit, spacecraft to test mass. And we need to combine them all, and then combine them for TDI to get the final results. So basically what we use is this multi-step algorithm where we use intermediary combinations to slowly reduce to the problem I presented before, and then finally suppress laser noise by computing, for example, X, Y, and Z. In the larger context of L0 to L1 pipeline, there's actually other stuff we need to do. Other noises need to be suppressed. This infamous tilt to length, or anything that has to do with imperfect clocks. The light travel times, which enter those delay operators that we use, needs to be estimated to exquisite precision. And of course, the data that we get in the end needs to be synchronized to a single time frame that people can use for data analysis and science. I think I'll say just one word about clock and time-related issues. So LISA, actually the measurements that comes out of LISA are beat notes, right? Because we use heterodyne interferometries. So we need to pinpoint microcycle phase shifts, which are due to gravitational waves, inside 25 megahertz peak nodes. And basically it means that you need an extremely high timing precision to be able to access these microcycle phase shifts. And existing space qualified clocks basically are just not good enough by several orders of magnitude. So we need to fix that. And in the end, we need several ranging measurements and we have strong requirements on them. Typically, we need inner spacecraft precision so that we can correct for this clock noise, the relative jitters of the clock. We need the inner spacecraft accuracy of about 10 nanoseconds so that we can do laser noise reduction to the expected levels. And in the end, we also need some kind of absolute accuracy with respect to a global time frame so that we can give you guys an L1 data set, which is time-stamped according to something you know. And there's multiple ways to do it, but basically we can combine multiple measurements to estimate these quantities. There's mainly 3 measurements we do. The clocks are used to modulate the laser beams that we exchange between the spacecraft, and that creates sidebands. We also modulate pseudo-random noise codes on top of it so that we can compare the phase values of the clocks. And of course, we can also observe the spacecraft from the ground to estimate the position and velocities. And the idea is to combine these measurements to get the best estimates of the clock and ranging quantities. There's another way to do it. It's called TDI ranging. And the idea is basically to fit these ranging quantities by minimizing the noise in the TDI combinations. And you can show that the laser noise suppression is maximal when one uses the true delays. Another way to do it, you can inject calibration tones and try to minimize the power on these calibration tones. You can see some results here applied on Bayesian framework by Page in 2021, and calibration tones that look like bunny ears on the right side by Stab in 2025. There's also there's been a parallel talk about it by Kohei, trying to carefully formulate TDI in terms of these delays. And the last thing I wanted to touch on is this tilt-to-length. Tilt-to-length is just a noise or a coupling between the laser beam tilts and optical element misalignments. And this basically gives us path length changes, aka phase shifts, that we can mistake for gravitational wave signals. We expect to do some compensation in hardware, but the residual that we expect from that still exceeds requirements. So one way to deal with it is to come up with a linear model. So 24 coefficients relating the tilt angles of the beams to the path length changes, and fits them every day using the data. That would be part of calibration. So that's also part of this L0 to L1 pipeline. And you can see on the right that if you do this, you get residuals that are below requirements. Another option, of course, is to do dynamical injections in your spacecraft to try to have a better calibration of the instrument. And there's there's been two parallel talks about TTL. One which is about subtraction of TTL in post-processing, and the other one about dedicated injections for TL2 length calibration. Okay, so that's the baseline pipeline. Probably it will work fine, we hope so. That's what we're developing. But there's a completely different way to look at it. Romano and Woan in 2006 suggested a new approach. In the frequency domain, you're free to do a principal component analysis of your noise, and you find the eigenvectors with the low eigenvalues, meaning low noise variance. And these are equivalent to TDI combinations, right? These are the laser noise free or almost free observables. If you do this, you're free to write down your likelihood directly in terms of phase emitter signals, as long as you correctly project your data onto those low variance combinations. It's been extended in 2021 for a more realistic model, and Baggy et al. Performed a full parameter estimation, I believe, for Gallic binaries. And you can see results on the right side. They have another paper where they showed that they can also infer the arm lengths, the delays, a little bit like TDI ranging, with this method as well.
Jean-Baptiste, just giving you a heads up, we're a little over time, so if you could wrap up quickly, then
sure, I think this is my second to last slide. A counterpart of that in the time domain, instead of doing that in the frequency domain, you're also free to model how your laser noise and other noises enter your measurements in the frequency domain. So you need to find a discretized description. And then you're free to find the null space of that mixing matrix. And these gets you the laser noise and other noise-free quantities. Of course, now there's no assumptions on stationarity of your data and model, so you can accommodate any arm length variation, and that's why it's called TDI infinity. You can see an example of parameter estimation on the right side. When I say nothing is assumed in terms of stationarity, it also means that it can gracefully handle data gaps, so a kind of non-stationarity. And that's what you see on the right side. There's a talk about principal component interferometry by John Baker. I think it was on Tuesday. Okay, takeaways. Of course, all these ideas needs to be tested. It's been done with numerical simulations. There are ongoing activities at DDPC, so the European, let's say, side of data processing, to develop and validate these L0 to L1 pipelines. And there are also a lot of prospective activities inside the consortium instrument simulation and processing group. And there's also a lot of tabletop experiments trying to check that laser noise suppression behaves as expected and that clock noise suppression also works, and so on and so on. This is, I think, the most recent example of a tabletop experiment or demonstration of clock noise suppression. A couple of talks related to this and perspectives. As I said, some of the questions are still active fields of research. What is the best choice of your TDI combination for data analysis? Can we use alternative? And so on and so on. And just a key takeaway, this L0 to L1 pipeline contains more than just TDI. I haven't talked about instrument characterization, data flagging, and low latency pipelines that we also need for fast detection alerts. These are ongoing in DDPC and the NASA Science Ground segment. And I think that's it for me. Thank you.
So we have time for maybe one quick.
Hey, Jean-Baptiste, it's Neil. Really nice stuff. One of the things, of course, when we do the analysis, we have to apply the same TDI delays to the signals, the waveform models. But there, this exquisite, cancellation requirements aren't needed, so you can be way coarser in how you handle the modeling, putting TDI onto signal. So, you can make that way faster, and it doesn't have to be a big block in the analysis. So that's, the requirements for suppressing noise are just gazillions of orders higher than what you need to worry about for the signal response. So, just something to keep in mind when you're actually putting together an analysis.
All right, let's thank Jean-Baptiste again. So our next speaker is Bogumiła Świeżewska, and she's going to be talking about probing symmetry breaking in the early universe with LISA.
Good morning, everyone. Can you hear me well?
Yes.
Okay, thank you. I'm very glad to be able to join you remotely from Poland, so I would like to thank the organizing for giving me this opportunity. On Monday, we have heard an overview on cosmology with LISA by Chiara Caprini, and in my talk, I would like to zoom in on one of the issues that we can study using LISA data, namely phase transitions in the universe related to symmetry breaking. So let me start with a short motivation. Why do we even care about phase transitions? Well, we know from the experiment, from the LHC, that the Higgs boson exists, and we know that its properties conform with the properties predicted by the standard model, namely that it couples the fermions and gauge bosons with a coupling that is proportional to their mass. This means that most likely the Higgs mechanism is operational, and it means that there is a scalar field which oscillates about a minimum which is not localized at the origin of the field space, but at some non-zero vacuum expectation value. On the other hand, we know from theory that at high temperatures, due to the interactions between the Higgs field and the plasma, the shape of this potential was changed to be symmetric. And then the scalar field had no other option but to oscillate about the symmetric minimum. And then as the universe cooled down from the initial hot phase to today, the scalar field must have transitioned to the current state. And this is the phase transition that, well, we know that happened, but we don't know any details about it. We don't know its properties, and we would like to learn more about it. So where on the universe's timeline is it situated? If we look at the history of the universe, well, we think it started with a Big Bang, then the universe cooled down and expanded until today. And this phenomenon of symmetry breaking that we are interested in actually is located very early in the history of the evolution of the universe, around 10 picoseconds after the Big Bang. So it is well within the region which the author of this graphic, which I took from BBC, labeled here as unobservable universe, unobservable past. Why? Just because it's not accessible with traditional astronomy based on electromagnetic radiation, because it happened before recombination. So the epoch that is now reached by James Webb Space Telescope is the epoch a few 100 million years after the Big Bang, but we would like to go to picoseconds after the Big Bang. And firstly, for us, it's not true that it's unobservable, because we really hope to reach it with the LISA detector through gravitational waves. So let me briefly review how a stochastic gravitational wave background can arise from a first-order phase transition in the early universe. And I should stress that I will be talking about a first-order phase transition, so one that is discontinuous. But let me give you some more detailed picture. So the object that is most important for us is the effective potential, a function that describes the energy of the scalar field. And as I explained before, at high temperatures, the electroweak symmetry is restored. But then as the universe cools down, a secondary minimum can develop. First, it is, well, not energetically favorable for the scalar field to move to this minimum, but as the temperature decreases, at some point the two minima become degenerate at the so-called critical temperature, below which a transition becomes possible. So the scalar field can either quantum mechanically tunnel under the potential barrier to occupy this energetically favorable minimum, or it can make a thermal jump over the potential barrier thanks to thermal fluctuations. When this happens, a bubble forms. A bubble filled with the new phase, a phase in which the scalar field has a non-zero vacuum expectation value, which is surrounded by the sea of the old phase, of the massless phase where the scalar still resides at the metastable phase. We consider a phase transition to start at the so-called nucleation temperature, with at least one bubble nucleates per Hubble volume. As the bubbles appear, they expand because this is energetically favorable, and then after some time they percolate, and we can consider the phase transition to be complete. So we know already that, well, during the transition, a first-order phase transition, bubbles are formed, and well, the bubble walls carry energy, right? Because the phase transition of transition, the scalar field of transition reveals energy from the vacuum, which is then used to accelerate the bubble. So we have accelerated movement, we have energy source, but what we still need to source gravitational waves is to break the spherical symmetry of the proton. But fortunately for us, there are more bubbles, not just one. And as the bubbles collide, symmetry is broken, spherical symmetry of the system is broken, and gravitational waves can be sourced. So collisions of bubble walls constitute the first source of gravitational waves that we can consider. But the bubbles do not expand in vacuum, they expand in the primordial hot plasma, and they interact with the plasma, generating acoustic waves. And those acoustic waves can again collide and source gravitational waves. After all the bubbles have collided and the sound waves decay into turbulence, the turbulence can also be a source of gravitational waves. In the most difficult scenarios, the sound waves are the most efficient source of gravitational waves. And in very strongly supercooled phase transitions, also bubble wall collisions can be significant. Now, how does it lead to a stochastic gravitational wave background? Well, in each Hubble patch, we have many of those bubbles, from a few to a few hundred. And what we see today comes not from a single Hubble patch, but from many uncorrelated Hubble patches. And therefore, a stochastic gravitational wave background is formed that we hope to observe in the future. How the spectrum is supposed to look like? Well, we know it based on simulations. I will tell you more about simulations in the next part of my talk. Here I present a sketch of such a spectrum overlapping the LISA sensitivity curve. And the shape of the spectrum is a doubly broken power law. And now I would like to tell you about some parameters that we can derive from the phase transition that actually influence the shape of the spectrum. So first of all, we have the phase transition strength, denoted as alpha, which basically tells us the energy budget of the transition. So the more energy released, the bigger alpha and the stronger the signal. Then we need some characteristic time or length scale. We can focus now on this parameter R star. You can think of it as mean separation of bubbles, or let's say average size of a bubble at the moment of the collision. The larger the bubbles, it means they have more time to grow and to gain energy, so the stronger the signal. So with growing R, we have stronger signal. You also need some characteristic temperature. Basically, that's the temperature from which the signal then redshifts. And therefore, this characteristic temperature sets the location of the peak. And last, we need to know the velocity of the expansion of the bubbles. It sets the length of this plateau on top of the signal. For ultra-relativistic bubbles, the size of the plateau will shrink to a point, and we will just have a broken power law as the template for the signal. So to sum up this first introduction, you can see that to get two gravitational waves from a phase transition, it's really a journey through different scales, starting from microphysics, where we need to describe the behavior of quantum fields at high temperature, and the bubble nucleation, through intermediate scales where modeling of plasma and bubble dynamics is needed, to the macrophysical scales at which we observe gravitational waves. And once we have data, once we measure gravitational waves, we can try to go the other way. So from macrophysical observations, we will try to infer about the microphysics. So this brings me to the next part, in which I would give you some examples of what we can possibly learn from the data once it is there. First of all, well, a disclaimer. In the standard model, the phase transition is a crossover. What it means it's a smooth transition where the field just rolls down the potential. There is no barrier separating two minima, no significant energy release, so we do not expect a gravitational wave signal there. Well, so our vanilla scenario is not probable, but on the other hand, it means that the search for a signal that is consistent with a first order phase transition is actually a search for new physics. So if we see something, we will have a trace of new physics. If we don't see anything, we will also be able to constrain new physics in a way that is complementary to collider search. What kind of phase transition can be observable if the phase transition within the standard model is not? Here I show you a graph from a paper quoted here below, in which the authors managed to map different kinds of extensions of the standard model, which feature a standard model-like phase transition into a single effective field theory. I will not give you the details of this process, just the conclusion. So here on the axis, we see alpha and beta parameters, which I have explained to you a second ago, the ones that determine the spectrum. And this gray region is the region which is occupied by predictions of different standard model-like scenarios. And the blue region, on the other hand, is a region where the signal-to-noise ratio for a signal in LISA can be above 10, so potentially observable. And unfortunately, you can see that those two regions are not overlapping, which means that if a phase transition is really standard model-like, you can observe it. However, there is this arrow that points in the right direction, and what it tells us is that we can predict an observable signal in models where beyond standard model degrees of freedom become dynamical. So I will be mostly focusing on this kind of scenarios here. And just to give you two examples, I would say there are two classes of models, of standard model extensions that can give us a phase transition. Well, here I call it ordinary versus superfold. So this left-hand side is as an example of an ordinary phase transition. It's for a model which is an extension of the standard model with an extra Higgs doublet. And again, the graph is in the alpha beta parameter space. The points here correspond to predictions for different parameter points of the model, and the colorful contour lines indicate the value of SNR. So you see we have some points that can be observable, but there are just some points. For most of the points, we actually don't see anything. This is maybe slightly discouraging, but well, it tells us that if we see a signal, then it will really constrain the possible scenarios. If we don't see anything, well, this will not teach us too much about this kind of model. The other plot here shows a contour plot of decimal logarithm of the signal-to-noise ratio for LISA, predicted in a model with classical scale invariance. So this type of model assumes that there are no dimension-pool parameters in your Lagrangian, which means that all the masses are actually generated by quantum effects. So they are quite different from the standard model, but still those models can be quite simple. So this example here is a model with an extra SU2 group. However, it only has two free parameters, one coupling and one mass. And so this is basically the whole allowed parameter space of the model. And you can see by the colors that in this allowed parameter space, the signal-to-noise ratio is generically very high, typically above 100. And this is quite typical to this class of models, not just this particular one. So what does it tell us? What it tells us is that if we don't see in LISA any signal that would be compatible with a phase transition, we can rule out this model. So even with negative results, we will be probing new physics models, and we will be able to falsify models. So we have those two complementary scenarios, and one is more, well, one can be probed with positive signals. The other can actually be falsified if there is no signal. So anyway, we will learn something about the possible directions in which we can extend the standard model. Well, but of course, signal-to-noise ratio is not the only thing that we can use to learn something. We can actually try to reconstruct the parameters of the spectrum, or even the parameters of the phase transition or the underlying model from a signal. here we have an example from a paper by the LISA Cosmology Working Group, where the injected signal was rather strong. I don't want to spend too much time on it, but I would like to emphasize one issue that appears, namely the parameter degeneracy. So changing the parameters of the phase transition, we can actually end up with similar spectra, because spectrum is determined by fewer parameters than phase transition. So there are degeneracies, and well, in the future one can try to break those degeneracies to get a better grasp of individual thermodynamical parameters. One that is already quite could be quite well constrained is the wall velocity, because this parameter determines the width of the plateau on top of the signal. Well, but if we go to more, let's say, exotic scenarios, so for example, super-cooled phase transitions that I have talked about before, or those conformal models, it can happen that the cosmological history of the universe is modified. So in this example, what happens is that the field cannot transfer its energy to the plasma right after the phase transition because its decay rate is very small. So this gamma 5 here is a decay rate, which leads to a brief period of matter domination after the phase transition, which in turn results in this feature in the spectrum. And now we ask the question, can we actually reconstruct this kind of feature? And it turns out that, well, given such a strong signal, we could. And what is interesting is that this feature is actually related to the decay rate of the scalar field, which is a parameter belonging to the realm of particle physics. And if this decay width is small, it's hard to probe it at detectors, at colliders, but then perhaps we will be able to probe it with gravitational waves. So again, a nice complementarity. One more example of what we can learn is that here I present you a reconstruction, but of model parameters. Back to this SU2 classically scale invariant model that I have presented before. So we inject the spectrum and we try to reconstruct the underlying parameters of the model, Gx and Mx. And now we have done it with two different methods, but not methods of reconstruction, but methods of determining the phase transition properties, so at the level of thermal quantum field theory. And what you can see in this plot is, first of all, that with such strong signals as we saw in the scale invariant models with SNR around 2000, we have great accuracy of reconstruction. There is no surprise here. So the width of this ellipse is very tiny. Probably the accuracy is at sub% level. But on the other hand, this theoretical uncertainty is huge, and it dominates over the experimental accuracy. But I have put here those quotation marks. This is not really an uncertainty. I would say that's a theoretical error if you don't use the most accurate method that there exists. So this brings me to the last part of my presentation, which should take the last 5 minutes, where I would like to show you just a very brief review of the recent activities in the field, how we try to improve the predictions. Of course, if one wants to improve, well, the efficiency of extracting knowledge from the data, one should also think of improving the reconstruction itself. But I will not cover it here in this talk because, well, I'm just working on the side of prediction. So that's what I can tell you about. So, and I will go according to the scales that I have listed before. So starting from the microphysics side, the crucial parameter here is the bubble nucleation rate, which is given by, well, an exponential decay formula with some prefactors. And the so-called statistical part of this expression is determined using thermal quantum field theory. And one needs a good handle of that to provide concrete results. And I will give you some examples on the next slide. And moreover, we have the dynamical prefactor, which captures out of equilibrium impact. And we can learn about that from simulations, which can also be used to check this whole formula. It's been theoretically derived, but one can simulate quantum fields to see bubbles forming and to check whether or not the rate agrees with theory. And there has been big progress in the very recent years. I have listed some papers here. And what we learned from those papers is that indeed this expression seems to be correct, it agrees with simulations. But to get to the agreement, we really need to take care of theoretical accuracy and pushing our computations to the correct order in perturbation theory. When it comes to handling quantum field at high temperatures, it's been known for many years now that the perturbative series is a bit more complicated than at zero temperature, because some diagrams of higher loop orders actually become comparable to the tree level. And this has been handled through some resumations. This has been very commonly used in the literature, but there exists an alternative method, also known for years, which was used to determine the character of the phase transition in the standard model, which is called dimensional reduction, which provides better estimates because it allows for systematically increasing the accuracy of your predictions. So it amounts to constructing an effective field theory, and then within the CFT, you can increase the order of your perturbative computations. So in recent years, this better method gains more and more popularity, also because a code has been published which kind of automates it, so we can do it more easily. Among other developments, we have, for example, constructed this kind of EFT for super cool phase transitions. So the ones that I have mentioned before that give us very strong transition. And actually this difference here between yellow and blue is the difference between using this daisy resummation that was on the previous slide and this better method. So you see, we really need to go for the best we have if we want to get all we can from the data. Moreover, people are generalizing those methods to go beyond the high temperature limit to account for different types of phase transition. When it comes to the bubble wall velocity, which is needed to determine the spectrum, it's a very hard problem because the velocity is determined by the balance of the pressure that pushes it outwards and the pressure from incoming particles. So particles that want to enter a bubble need to gain mass. So they have to steal some momentum from the expanding bubble. If that's possible, they enter. If not, they can be reflected from the bubble. And also some particles may try to escape the bubble. So to really solve for the bubble wall velocity, one needs to solve coupled Boltzmann equations for the system of the scalar field and the plasma. And in recent years, there has been a lot of progress also in different schemes for solving these equations and also approximate schemes. So we are getting better and better approximations to the wall velocity. And last but not least, we need numerical simulations to go from the thermodynamical parameters to the spectra. So here I show you some slices of a simulation from a paper quoted here from a few years back. So what people do, they simulate the scalar field bubbles and the plasma using relativistic hydrodynamics. They evaluate the energy momentum tensor, compute the power spectrum of gravitational waves, and create a template that people like me, for example, they then can use to match the predictions from models. But to have accurate spectra, well, people need to advance the simulations, and this has been done in many ways in the recent years by accounting for stronger transitions, which are harder to model, accounting for effect of gravity for large bubbles, modeling the turbulence better, developing long-lasting 3D simulations, and much more. So there is a lot going on in this business. Okay, let me just summarize. So first and foremost, LISA will probe the early universe at the scales of picoseconds, because whether or not we see a signal compatible with a first-order cosmological phase transition, we will learn something. Either we will constrain models, or we will falsify models, or we will actually be pointed to some very specific scenarios. So in any case, we will really learn something. And searching for gravitational waves from a phase transition, as I told you, is searching for new physics. So we hope for complementary probes, complementary to what we do at colliders. And moreover, as I hope I convinced you, the prospect of LISA data stimulates theoretical developments to model the predictions, and I hope that in the next decade to come, we will really master our predictions to be ready to face data. Thank you very much for your attention.
Maybe, is Joey here? If you start making your way up. We have time for a quick question while Joey gets set up.
Hi, Bogumiła, this is Shane. Thank you. That was great. I have maybe a naive question. So you talked here at the end especially about kind of progress on the theory front that will help us as we move forward. I'm wondering, are there other constraints that are going to happen in the next 10 years, either from accelerator experiments or other parts of the gravitational wave spectrum that will help guide us as we start thinking about doing this kind of work with LISA?
Thanks for your question. Well, yes, of course. So on one hand, we already have the PTA data that I did not mention, but actually as people try to, explain the signal, a signal from a phase transition, according to some papers, is the best match. I would claim we still don't know, but it could point us towards some direction. Of course, if it's a phase transition as it's seen by PTA, well, it will not be seen by LISA because it's a different frequency band, but it could tell us that, well, such phenomena actually happened in the early universe. And then there is complementarity, let's say to some extent, between studying the Higgs potential with colliders and with gravitational waves, because if you want a first order phase transition, you need a barrier between the two minima. So you need to change the shape of the Higgs potential. So in principle, this could be probed by LHC. As far as I know, by the end of the LHC run, we will not have great accuracy on the Higgs self-coupling. So we would probably need to wait maybe for the next, for the high luminosity LHC. And also this problem that the standard model like phase transitions are not observable, I think it casts some doubt on the prospect of it, but we can of course try. What more? Well, we will be probing some long-lived invisible particles in detectors, which could then show up somehow in those models that we study. So there are some maybe less obvious points in which you can see cross correlations, let's say.
All right, well, let's thank Bogumiła again. All right, and last but not least, we have Joey Shapiro Key talking to us about gravitational wave observatories from the ground to PTAs.
Great, thank you. Can you hear me? It's working here, yeah. Okay, great. Shane asked a good question, right? What else can we talk about after we've been talking about LISA all week? What else, what other kinds of questions do we have about what we know and what we can know? We're going to spend a little bit of time here talking about the gravitational wave observatories here on the ground and pulsar timing arrays and what we expect in through the 2030s. So when we have LISA. So on either side of the gravitational wave spectrum from LISA, are our ground-based experiments, LIGO, Virgo, COGRA right now, and then we'll talk a bit about the plans for next generation observatories on the ground, and then the pulsar timing arrays, what's going on now and what do we expect in the 2030s when we have LISA. Our current gravitational wave observatories on the ground, LIGO, Virgo, and COGRA. We have observatories in the US, in Europe, in Japan, and a future detector in India, LIGO India. Also already thinking about what will be the next generation of observatories on the Earth. So in the 2030s, we expect Cosmic Explorer here in the US. This is the National Science Foundation, NSF selection for an observatory in the US. And then Einstein Telescope in Europe. Little twiddles on the years there because these are long-term plans and projects, but aiming to observe in the 2030s together. So still a worldwide network of observatories. Obviously, it's complicated to have these size of projects, but ideally observing together in Europe and the US in the 2030s. What do we already see with our ground-based detectors? The gravitational wave transient catalog, the GWTCs, recently GWTC5, observing lots of black hole mergers and some neutron star mergers and neutron star black hole mergers. Probing the population of black holes that are out there in the universe up to right about that 200 solar masses, right? So these are our stellar mass black hole merger population being observed by the ground-based detectors. And starting to look at now that we have so many, almost 400 mergers, population properties of merging compact binaries. I'm also out with the catalog, looking at analysis of what is the population of black hole binaries out there, with some potentially interesting features that currently persist in the data. That you can see around 10 and 35-ish solar masses. As we get more data, we learn more about the population of black holes. Now, the next generation, sometimes called XG for next generation gravitational wave observatories, ground-based, so here on Earth, will probe out to much higher redshift. So thinking about the increased sensitivity for new detector technology, and certainly in the case of Cosmic Explorer, up to 40-kilometer arms, so 10 times larger than the LIGO arms. We get to probe out to much higher redshift, and then that volume, that increased volume of observing black hole mergers and compact binary mergers. Sorry. We also expect potentially lots of neutron star mergers as well. Okay, so Einstein Telescope is the project in Europe. Probably many of you are members of the project. They're talking about the detector architecture and have identified some potential sites and are still at sort of this phase of figuring out what it will look like and where it will be. I know a little bit more about the status of Cosmic Explorer since I work with them. This is the National Science Foundation selection for the next generation observatories here in the US. Here's a nice sort of architectural concept. We're in the conceptual design phase, already working with designers and architects, technology development, and thinking about where could you put an observatory with 40-kilometer arms here in the US. Thinking about where that could be in the lower 48 US. It would be so the facility itself will be bigger. There will be more people working there, and then also the arms will be much longer. You need roads and wildlife bridges, and it's a big project. And in the U.S. and everywhere, the land that you want to use to build an observatory is populated currently and historically by people. And so already we're thinking about what is it like to, building relationships, talking to people, figuring out, who's interested also in land that astronomers are interested in. And so it's a priority of the Cosmic Explorer project to already be making contacts and building relationships with native communities and local communities that would be part of the observatory once a site is selected. This is important in astronomy historically and certainly today. So let's look a little bit at the Cosmic Explorer location search. So this is interesting. It's a interdisciplinary team thinking about where we can put a big facility. So here we have some pink blobs that are national suitability site work. So looking at places in general where you could have a facility, where people could live, where your workforce would have access to education and healthcare and food and all of this. And then there's some colorful, funny shapes that are looking at cost and location analysis. And so you can start to see they're actually like putting down the arms, so the 40-kilometer L shapes in lots of places. The different colors don't really matter, but you can see the funny shapes from where they're trying to put some arms. For instance, over here in Oregon, nope, that's not what I wanted. I wanted this. In Oregon, right, you can see it sort of works to put some arms that way and that way, yeah? And then it also overlaps with some of the national suitability analysis, which are the pink blobs. So you can start sort of looking for places where they overlap, and there are some options, and so the team is already spending some time in those places, talking to people who are there, starting to do some local measurements, things like that. So, right, you can use sort of public national data to do an initial analysis, but then you eventually need to go there and be on the ground doing local measurements and meeting people. There's a publication on the archive if you want to know more about how that's going, but it's certainly fun to look at the maps. Okay, we also can compare the sensitivity curves for our current observatories. Here we are in 05 for the current observatories. Potential instrument upgrades into A# in the green there, and then Einstein telescope a Cosmic Explorer 20-kilometer long observatory has been in the discussion, so that curve is also on there. But an independent panel recommended to NSF a 40-kilometer Cosmic Explorer observing jointly with the Einstein telescope. But the site selection does currently include also looking for potential 20-kilometer Cosmic Explorer sites. Okay, what else will be going on in the 2030s? Well, one of our favorites here, LISA data in the 2030s. Also, next generation neutrino observatories. So now we're really talking about some exciting multi-messenger potential. The electromagnetic band. Also, we can be thinking about what facilities will be operating in the 2030s. Krista told us some, yes, about X-rays. The picture is that, right, we hope to have increased potential for multi-messenger observations. But because these facilities and projects are so long-term, we're sort of, already things that are on their way will be what we'll be able to use during LISA data. Okay, I also want to talk about the pulsar timing arrays, so including nanograv, where we use pulsars in our galaxy, observe them with radio telescopes here on Earth to detect nanohertz gravitational waves passing through this array of pulsars in our nearby galaxy. So for nanograv, the data releases and results come out at somewhat regular intervals. The most recent being the 15-year results that we'll look at a little bit, but to show you that we observe pulsars for a long time, so for decades, and also add new pulsars to the array for each of the PTA data sets. So in the summer of 2023, the nanograv 15-year data set results were released, showing evidence for a gravitational wave background in the nanohertz. And what that looks like is that the correlation strength for any pair of pulsars in this array of pulsars in our galaxy, you can look at their separation angle, and there's this characteristic shape called, predicted by Hellings and Downs, called the Hellings and Downs curve. And here, this is showing the nanograv data following that characteristic shape of correlation strength versus the separation angle of each of the pairs of pulsars in the array. And we work as part of the International Pulsar Timing Array. They're actually meeting also this week in South Africa. Working hard on the International Pulsar Timing Array. Hopefully they're also talking a little bit about LISA, since we're talking about them. You can see the nanograv is a member, also the European Pulsar Timing Array, the African and Pulsar Timing Array, the Indian Pulsar Timing Array, Chinese Pulsar Timing Array with the FAST telescope, and the Parkes Pulsar Timing Array in Australia. And together, the pulsar timing arrays can do joint analysis And this is more data and good joint analysis is the ideal science we can do. So this is comparing the sensitivity curves for nanograv ePTA plus the Indian PTA and the Parkes pulsar timing array compared to the joint median result for the nanohertz gravitational wave background. And then also looking at the parameters for that background, the amplitude and spectral index, and the joint analysis agrees and also overlaps with a spectral index of 13/3 for the gravitational wave background. We'll continue to characterize that background, that nanohertz background, and also look for individual sources of gravitational waves. So this will be what is coming up for the pulsar timing arrays. Crystalline Smith shared this slide showing some of the candidate sources from electromagnetic astronomy for massive black hole binaries that would be close enough to be emitting nanohertz gravitational waves. And so if we can do directed searches for those candidates as well as a general search and an all sky search. But you can see on the sky map, the sky locations are these diamonds for the candidate binaries and how well we can look for those candidates as the sort of some of the initial analysis for looking for individual sources of nanohertz gravitational waves. So that's what's coming up for the pulsar timing arrays. So in the 2030s, the sensitivity increases just with the time baseline, also with new pulsars and improved analysis. So we'll continue to characterize the background, actually looking for anisotropies and such. Also, sensitivity potentially to individual sources, continuous wave sources in the nanohertz. We also looked at the increased sensitivities we expect for the next generation of ground-based detectors, Einstein Telescope and Cosmic Explorer, continuing to probe that population. And then, of course, we expect LISA data in the source-rich millihertz band. So it will be an exciting decade. We're looking forward to really lots of science that we can do. And then, of course, also with our multi-messenger partners to really do as much science as we can. Who will be those scientists in the 2030s, right? It's our, some of us hope to still be around, but certainly the early career scientists, right, will be leading the way. And the early career scientists are already joining forces across the collaborations. So Deborah told us about the LISA early career scientists and their connection to the gravitational wave early career scientists with lots of activities that they do really across the collaborations. So we see it in their groups, but we also see it as students and postdocs and faculty are work and are trained in one collaboration, but are also interested in what's going on across the gravitational wave spectrum and across the gravitational wave band. And so that really is a great thing about our community and our science. So just to say that we have lots, there's lots to be done, and it's fun to do the work with all of you. Thanks.
We have time for a few questions, actually.
Joey, when is the next PTA release?
The 17 and a half years, is that right, people? 20.
20? I want to know. Okay.
Question over here.
But we're only a couple years into it. Yeah.
There's a question over here.
My question is about the Cosmic Explorer, as you called it. What kind of legislation would a state government have to pass to get it built in their state, especially if that state is Illinois?
Okay, there's, well, one of the issues with Illinois is that it doesn't have a pink blob on it. So there are some sort of cost and location analysis identified there, but it didn't sort of fit all the analysis. But the question is still relevant. You know, who's involved when you build a big facility like this? And it's certainly state and local governments, but it's also federal, because it's NSF federal funding, and then also the local communities, and also the native nations who are independent governments. And so it's really quite a lot of work. That's why that work has already started.
That's sort of where state government came in. It's possible that the government of Illinois could give some money, and also as far as indigenous people are concerned, right by St. Louis, there is a old city called Cahokia. It's where the Mississippian culture was centered. If we want to talk about indigenous people, their entire culture was based around astronomy there. And it's a bit more complicated in that we know in historical times different tribes and nations inhabited that area, so it's hard to say exactly whose culture would reign supreme in that. It's a complicated issue. But talk to me. I know people in state government, maybe we can figure out a way to make that blog pink.
More suitable. Right, but that's an excellent point. That's right. It's not just who is currently living on the land, right? It's also connected to people who were moved away and things like this, right? So anywhere you look in the U.S., that is often the case. And so yes, people are already paying attention to this, and it's a very complicated landscape. Yeah.
Speaker, right over there.
There's an online question that is, what is the situation of funding for Cosmic Explorer?
Cosmic Explorer is currently funded by National Science Foundation at the conceptual design phase. So there's a little bit of funding for a handful of universities in the US doing this conceptual design work, including working with architects to make, oops, I went the wrong way. You know, to really think about, you know, what it would look like, and doing costing estimates and things like that. So I would say it's low-level funding from the NSF, but for this conceptual design phase. The idea is that when it moves into the design phase, there would need to be more substantial funding to actually make sure the technology is ready and things like this.
Could you talk a little bit about localization, since we'll be going from 2 LIGO sites, which I assume we're still running, but we'll only have 1 Cosmic Explorer in the U.S. What's that going to do to localization of signal?
Yeah, the idea is, so the recommendation, there was an independent panel that made a recommendation to NSF about the selection for Cosmic Explorer, and the recommendation was, if there's Einstein telescope observing at the same time, then 140-kilometer CE works as a global network for localization and uptime and observing. If, for whatever reason, there is not Einstein telescope, then the recommendation is to have 2 observatories in the US, the 20-kilometer and the 40-kilometer.
All right, so last question here for Scott.
Yeah, so this is back to Cosmic Explorer and the locations. So, I mean, there are national politics involved because, like, George Bush was instrumental in getting the superconducting super collider in Texas, for instance, when he became president. Yeah, so I see a lot of pink where there's a lot of fracking. And I know Livingston had problems with the local logging industry. So I'm sure this is being like investigated and stuff, but like, could you speak to maybe more about that?
Yeah, there's some open land in Texas, and there's some, we actually look for like bowl-shaped areas because of the long arms and the curvature of the Earth. And there's some areas like that in Texas, sort of these ones over here, and actually also this one down here where we have some colleagues. And so we have gone to visit, actually, to do some more exploration of, you know, what would it be like to have observatories there. And fracking is one of the major issues. And there's lots of things to consider, and I would say those are not likely sites in Texas there.
All right,
Yeah.
don't rush off the coffee quite yet because we have some announcements. Let's thank Joey and all the speakers again.